Hello, thank you. My name is Anat Siddharth. I'm a PhD student in the group of Professor Tobias Kippenberg at EPFL in Switzerland. I'm here to present our recent work on ultra-fast tunable photonic integrated extended DBR Pockels laser. So low noise lasers are critical components for various applications such as optical ranging, sensing and spectroscopy, OCT, coherent communication, photonic computing, etc. And the requirements to address such applications, the laser system are critical components, and they require features such as low noise, narrow line width, high speed frequency agility, wide tunability, higher output power, low cost. And over the years, a lot of research has gone into develop such lasers, which has resulted in many, more than 15 Nobel Prizes. But ever since, there has not been a universal size, weight, power, cost, effective solution. And thereby, we have to come to a photonic integrated solution. So there are different approaches to hybrid integrated lasers. One of them is self-injection locking, where there is a laser that is locked to a high Q microresonator because it receives a feedback at the resonance of such a cavity. There are various advantages to this approach, such as it has high frequency stability and low noise. It has lower relative intensity noise, but of course it comes with certain cons, such as limited tunability, precise operating parameters, because you have to align with the resonance of the microresonator, low output power, and mainly for a very low noise laser, it is DFB based, which increases the cost of such lasers. Then it comes the external cavity laser approaches. One of them is the vernier filters, which provides higher frequency tuning range as it is proportional to the vernier FSR. It is cost effective because it's based on RSOA. Reflective semiconductor optical amplifier, and it has lower power consumption. But again, you need to align two cavities. You need precise operating parameters, and because you have two optical cavities which will absorb some powers, it will have low output power and higher line width and relative intensity noise. The approach that I will discuss here will be about Bragg gratings, which provides wide tuning range. It basically makes your laser turnkey operable. It has high spectral purity, higher output power. Again, it is RSOA based, so lower cost and lower relative intensity noise. But of course, it is sensitive to optical feedback and also to fabrication, as you need to design your gratings to a specific period. The main motivation of using the external DBR approach is to get fast tunability with high output power and turnkey operability. Now, with regards to the actuation of photonic integrated circuits, there are again multiple approaches. The primary one is using the metallic heaters and modulating your refractive index via thermo-optic effect. So there is no material limitation. Various metals can be used. You can provide large tuning range, but again, the tuning will be unidirectional. It will consume a lot of electrical power and has lower actuation bandwidth up to tens of kilohertz. Another approach is to use test optic effect, and our group has done a lot of work in this field too, where it provides higher actuation bandwidth. We can use wide choice of material, the piezoelectric material, which is monolithically integrated on the vertical photonic stack. You can use aluminum nitride, PZT, but again, there are certain disadvantages with materials like PZT, as it has low breakdown voltage and a large leakage current. So it does not become very power efficient. And the approach that I will discuss here is about electro-optic effect, where we can have very high actuation bandwidth, can have large tuning efficiency up to of gigahertz per volt, but of course it is limited to electro-optic materials. So of course I don't need to introduce a lot about lithium niobate integrated photonics, but this field has grown over the years, and lithium niobate with its unique properties such as second order nonlinear coefficient, which has given application in quasi-phase matching, high Pockels coefficient, has developed modulators, and there are also piezoelectric strain coefficient, where research groups have demonstrated acousto-optical devices based on lithium niobate. Our group specifically has developed a fabrication process for fabricating lithium niobate photonic integrated circuits, that we have developed a platform for high density lithium niobate on insulator photonic integrated circuits, which is based on deeply etched strip waveguides with tight optical confinement, and we use amorphous film, diamond-like carbon as hard mask. And as a result, we can fabricate high-yield, ultra-low loss, less than 4 dB per meter photonic circuits with very high area density. And because of DLC as hard mask, we have high etching selectivity and smooth sidewall with wafer-scale uniformity. Now, talking about the laser that the subject is about. So we have designed a distributed Bragg reflector. So basically, that is a Bragg grating, which is a periodic variation of refractive index, and that creates a wavelength-specific mirror, and which helps to make a laser. So here, basically, you can see on the slide how do you calculate the Bragg wavelength, the coupling coefficient, which is basically the Fourier transform of the refractive index profile, the peak reflectivity, and the reflection bandwidth. All are those critical parameters that you need to study before you design the laser. So for specific laser design, the thing to keep in mind is that you need lower reflection bandwidth, but higher reflectivity. And you need to design your grating period within the fabrication tolerances. So you can see that your coupling coefficient is directly proportional to your reflection bandwidth. And therefore, to have lower reflection bandwidth, you need lower coupling coefficient. You need very weak perturbation of your refractive index. But at the same time, you also need higher reflectivity. So you need weak perturbation of refractive index, but longer gratings. So, but in order to have a approach of photonic integrated circuits, we wanted to make the size, we wanted to keep the size compact, and therefore we designed our structure with post gratings to have weak perturbation, and we fixed our length as to 7 millimeters. But then this is not a square wave grating, so we had to analyze the coupling coefficient, and also from the graph you can see that we can change the gap, the post gap, the circular post that you see, we can change the gap and thus vary the coupling coefficient, and also with changing length we can increase the reflectivity, so we can have the desired value according to the size of a photonic circuit. So since our design is with circular post, our refractive index profile looks like this, and if you do the Fourier analysis, and you can see on the right side the Fourier transform of the refractive index profile, you can see that if you have a 50% duty cycle square wave refractive index profile, then basically all your even harmonics are null. So you won't get any second order, fourth order grating. But with such a profile, you can definitely get second order, third order change in refractive index. Thus, there is some coupling coefficient from your Bragg gratings. So for fabrication tolerances to be within the limit, we designed our for third order Bragg grating, and with silicon nitride platform, we are actually used second order. So this is our design on of the ultrafast tunable photonic integrated extended Pockels DBR laser based on lithium niobate, thin film lithium niobate. Here you can see that we have a photonic chip of 7 millimeter long with uniform grating posts that are placed on the either side of the waveguide with third order period to obtain reflection at the Bragg wavelength of 1550 nanometer. The grating post, this provides weak perturbation in refractive index, and that can be controlled by changing the gap of these posts, as I mentioned earlier. And on the either side of the facet, you can see that we have designed horn-tapered optical couplers to couple efficiently with the RSOA, and on the other side, to couple light out into the lens fiber, we have a tapered optical coupler. So this is basically the SEM that you can see of our waveguides. So on the we can see that there are non-buffered gold electrodes for better actuation efficiency and lower DC drifts compared to the buffered electrodes. As you can see, there are no cladding on top of the electrodes. And on the left, you can see that how the simulated reflection tuning, that if you apply 19 volts with this particular configuration of your electrodes, you can basically get up to more than 10 gigahertz of tuning. And now coming to the experimental characterization of a laser. So on the right, you can see the photograph of a 10 millimeter by 5 millimeter chip with 40 such DBR waveguides. And on the left is basically the characterization of both the tunability and the laser characterization. So here you can see the LI curve, the frequency noise power spectral density, and the output power spectrum with the side mode separation ratio of very high side mode separation ratio of 63 dB. You can see here that there are noise is basically at lower offset frequencies. It increases with the slope of around with f to the power minus 1.2 to the minus 1.5, which is limited by the thermal charge carrier refractive noise. And this is consistent because we have discovered this in a separate work, which is now going to be published in Nature Physics, which is basically, we established that it is the electrical Johnson-Nyquist noise, which is the fundamental limitation for Pockels integrated photonics. But nevertheless, the intrinsic line width is around 2.8 kilohertz, which is good enough for various applications. And now to demonstrate, and also I want to highlight that with only low current of around 250 to 300 milliamps on the RSOA, we can get output power of more than 15 milliwatt from this photonic integrated laser. So now to show you the ultra-fast tunability, so here you can see that we have modulation speed up to 1 megahertz, and we can get tuning range greater than 10 gigahertz. And to demonstrate even the high tuning speed, we mimic the logo of EPFL from an arbitrary waveform generator, and then you can see that the laser frequency evolves with the same in the same fashion, and that translates in excess of 3 petahertz per second tuning speed, and with more than 10 gigahertz of tuning. And actually, our tuning speed is limited by the probe electrodes and the voltage amplifier. Now, to characterize the actuation bandwidth of our DBR gratings, because the linearity of the tuning range is dependent on the actuation response of the device, and it is very ideally a very flat actuation bandwidth desired for applications such as FMCW LiDAR. So here on the left, you can see basically the grating reflection tuning as you apply voltages. So we can see that the grating reflection is tuning by 10 gigahertz if you apply around 10 volts, and you apply 20 volts. And here is the characterization of the actuation bandwidth, where you can see that there is a flat actuation response up to 10 megahertz with a deviation of 1 dB over 10 megahertz, and it is actually limited by the bulk acoustic resonant mode at 19.8 megahertz. And now, when we have this ultra-fast tunability, we use this laser to demonstrate a centimeter resolution FMCW coherent ranging experiment in lab, where we have very small pedestal post with such small holes, and with no pre-distortion linearization, just turnkey LiDAR engine, and we can get less than 5 centimeter distant resolution, and can easily also map the point cloud of the target scene. And again, because to have very specific absolute reference calibration of our tuning range, we did HCN gas spectroscopy. We packaged the fully hybrid integrated Pockels E-DBR laser, which just can operate with turnkey, which has frequency drift less than 100 megahertz over 25 minutes, and we can observe the absorption spectrum of the HCN around 1545 nanometer, and which is in good agreement with the HITRAN database, and it confirms the high tuning range. So in summary, we have the first demonstration of a turnkey low noise Pockels E-DBR laser with intrinsic line width of 2.8 kilohertz with unprecedented ultra-fast tunability of more than 10 gigahertz tuning range and more than 10 megahertz actuation bandwidth, and we demonstrated centimeter resolution FMCW LiDAR and HCN gas spectroscopy. So the devices were fabricated by Luxtelligence. You can visit their booth here in exhibition. We also have other spin-off from our labs, which are all present here in the ECOC exhibition, Deep Light, which is an ultra-low noise frequency-agile photonic lasers based on silicon nitride, and Edwatec, which provides erbium-based photonic integrated erbium-based amplifiers. Thank you.
Thank you very much. I'm sure there are many questions, but